Bum, 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 bum. Are you ready? We're going to start class number 4, and we are going to explore combinational logic. Now, this is pure logic such that the output of the system is 100% dependent on the input. The implication being that there is no memory associated with this circuit. For example, you may have seen this circuit in the lab. Does that look familiar? Where this is a K1, we'll call this K1. This is the start button, and this is the stop button. Okay, that's a seal-in circuit. That is not what we're talking about. We're talking about combinational logic, where the output is purely dependent on the input. So if the inputs change, the output will change. And that is not what happens here, because this circuit has memory. We'll talk about that another day. Our first example for combinational logic is this. We have 3 inputs. We're going to call them Boolean C, Boolean B, and Boolean A. They are going to control Boolean F. And we would call these, let's see, we would typically call these contacts. In fact, we could call them normally open contacts. I'm going to put that in parentheses. I'll tell you why in a moment. And we would call this a coil. You may recognize this as a 3-input AND logic. And I'm going to write something.
We would say that the coil XF will activate when contacts Boolean C, Boolean B, and Boolean A are all closed. You notice I'm using a lot of quotes.
All right, so I mentioned the coil and I mentioned activate and contacts because it's an analogy. That is not what's happening inside the PLC. There are no coils at this point when you're programming. Remember when we emphasized the system scan? At 12 o'clock, we had system maintenance where the PLC took care of itself. At 3 o'clock, it went peekaboo and it grabbed all of the inputs and put them into a memory location. At 6 o'clock, we have your programs, which are under your control. We have a mapping of inputs to memory locations. We have your program, which is a memory-to-memory operation. And we have output map, which is a mapping of memory to screw terminal outputs. On the output scan, the PLC actually transfers those memory locations to the outputs, to the screw terminal outputs. And of course, this goes round and round again many thousand times a second. We looked at it this way, where we said our in-map is a screw terminal to memory transfer. We talked about program control being a memory to memory transfer, and we talked about program outmap being a memory to screw terminal transfer. And we are operating right here for our entire lecture. It's memory to memory. There are no coils, there is no activation, there is no contacts. It's memory to memory. If you want to get technical about it, we need to draw a cartoon. So we have a memory location here, and our job is to look at that memory location. Over here, we have a switch, and we can put that switch into one of 2 positions. We can put it into the true position, or we can put it into the false position. And then we send that information out. If we put this into a box, we can give that box a label. We'll call it the examine if closed function. And at this point, we need to give ourselves a rule. So what is the rule that we live by? Inside, we would say we have a memory location. So we look at the memory location, right? So you look here. What is the memory? Based on the memory, you'll set the output lever. If the memory location is 1, the output is set to true. If the memory location that you're examining is 0, you set the output to 0. Okay? That's what's going on inside the PLC. We add another line here. Let's call it the enable. And let's call this the output. We call this the examine.
If closed function.
And the job of this person sitting inside is to look at the memory location. In this case, it's a Boolean memory location, so a 1-bit wide memory location, and ask, is it true or is it false? If it evaluates true, or if it evaluates closed, which is the same thing, if it's true, if it's on, if it's 1, if it's closed, all the same words, then this line right here is true, and the output will be set to 1. That memory location we speak of, it could be this tag memory. It could be the input image memory. It could even be the output image memory. But either way, we have this examine if closed function. It looks to a very particular piece of memory and then takes action. Back inside the PLC, we have 3 examine if closed functions. We will associate them with a particular memory, in this case Boolean C, Boolean B, Boolean A, and Boolean F. And what we will do is we will read and evaluate. So read and evaluate those 3 memory locations. And based on that, we will save the result. Where do we save it? Well, we save it in the memory location associated with the Boolean labeled F. Another way to look at this is to say we are going to take a walk on this rung. And we're going to walk in that general direction. So the first thing we do is we say, does the Boolean location C evaluate as true? If the answer is yes, then we continue on. Does the Boolean B evaluate as true? Yes, we continue on. Does the Boolean A evaluate as true? If the answer is yes, then a 1 is stored in this location. If, on the other hand, we walk through this path and we find that one of these evaluates as false, you could think of that as a fail. You end up falling off the rung, which means that this gets a value of 0 instead. Another way to look at this is to say, I have my meter. This meter is set up for continuity. So I attach one lead there, and then I put the lead there, and I say, do we have continuity across Boolean C? If the answer is yes, then we can move here. Do we have continuity across all of these, across Boolean C and Boolean A? If yes, we can continue on. Do I have continuity here? Right? Are all 3 of these closed? If the answer is yes, well, then we store a 1. Or excuse me. Yes, we store a 1 into that memory location. If one of these evaluates as false, right? So maybe you only get continuity to here, but you don't here. So we would stop and we would say, sorry, this is now going to store a 0 into that memory location. While we're on the subject, let's talk about reality versus the analogy that we've been using. One thing we could say in the real world is that
almost everything in the IEC 61131 environment is a function.
Just about everything. We've talked about the examine if closed function, right? That's this one. There's also an examine if open function, like that. The OTE function, did we mention that? I don't remember. That's the coil, right? The coil is a function into itself. And I know I've mentioned this before, and this is certainly the target of the class, is to hit those user-defined function blocks. right? That's going to be really important to us later on. Okay, so that's the reality. The analogy is that it's easy to visualize and troubleshoot ladder logic because it's based on the traditional contacts and coils. It's also easy to talk about the continuity that we mentioned.
For example, if C, B, and A are all closed, coil F is energized.
And now we make the uncomfortable admission that we are going to use each of these interchangeably. And depending on the context or depending on the mood of the author, we'll slide back and forth between talking about things like XIC or talking about the normally open contact. Sometimes we'll talk about an output enable function, and other times we'll just talk about a coil. All right, let's circle back and talk about the AND logic. We established that this was a 2-input AND gate. This is a 3-input AND gate. Yes, there is a limit to how many contacts you can use. I would argue that long before you run out of contacts, you're going to run out of the ability to keep track of everything. Because what will happen is your rungs will be so long and they'll start leaving the page, right? You'll have to move back and forth in your screen. It's very difficult to keep that straight in your mind. Okay, let's look at another one. So sometimes you can have AND gates that look like this. So we'll let this be Boolean C, Boolean B, Boolean A, and again, Boolean F is the coil. And we talked about continuity, right? What would it take to get continuity across this? Well, you could argue that that's a normally open contact, that's a normally closed contact, and that's a normally open contact. So you would need coil C to be activated, so that would have to be true, a memory location of 1, excuse me, the memory location pointed to by Boolean C would have to be 1. Boolean B would have to be 0 or resting, right, in its normally closed position. And Boolean A would have to be 1. And when you see this sequence, then the coil F will be written to as a 1. So we could call this true, we could call this false, we could call this true. Again, these are the conditions that you would need to establish continuity across this rung. So 1, 0, 1 is what it would take. We could put that into a truth table. Now there are 3 inputs, so I'm going to write this as Boolean C, Boolean B, Boolean A. And then I'm going to call this Boolean F. So we have 3 inputs and 1 output. So 0, 1, 0, 1. Draw a line there for convenience. 0, 1, 0, 1. 0, 0, 1, 1. 0, 0, 1, 1. You notice the pattern? For A, it goes 0, 1, 0, 1. So it alternates every other line, or every line. Whereas B, we have 2 zeros, 2 1s, 2 zeros, 2 1s. For C, there are 4 zeros, and then 1, 2, 3, 4 1s. Let's go back and look at this, and we see a pattern of 1, 0, 1. So right here is when that would evaluate as true. It would be false for all other conditions. Let's see if that makes any sense. Consider the first row in our truth table. Here we see the C input is 0. And right there, we're done. Because if C is 0, right, that's a normally open contact, there will be no continuity across it. So right there, we can see that none of these first 4, are all going to evaluate as 0. Next, we look at contact B. And we see that contact B, memory location B, however you want to look at that, must be relaxed, right? It must be in the normally closed position. So that means that those conditions must be true. This must be true. And now we're at A. And we see that contact A is normally open, which means it must be activated in order for this logic to evaluate as true, right? So that's this one right here. When we have a pattern of 1, 0, 1, that is the only combination of 3 inputs that will activate coil F. Let's talk about the size of our truth table. If the number of inputs is 2, the number of combinations with 2 input system is 4. If we have 3 inputs, there can be 8. And that's what we had here, isn't it? Right? We had 3 different inputs, C, B, and A. And we saw the truth table had 8 entries. If you wanted to be fussy about it, we would call this 0, 1, 2, 3, 4, 5, 6, and 7. So there are 8 entries in that truth table. These numbers, by the way, 0, 0, 0 is the binary representation of 0, and 1, 1, 1 is the binary representation for the number 7. If we have 4, there will be 16. If we have 5, there will be 32. You can generalize that and say that the size of the table is equal to 2 to the nth, where n is the number of inputs. Enough about truth tables. Let's talk about logic gates. This is the symbol for a 2-input AND gate. So this is an AND. We could sketch a 3-input AND gate. 1, 2, 3. Okay, 3, and you could continue on and have as many inputs to that AND gate as you would like. So logic gates. Let's talk about Boolean algebra. The AND is represented as the product of 2 inputs. Right? So this is a product. You may also see that as this, where it's B multiplied by A, or sometimes you'll see a dot like so. But either way, it's a product, right? So an AND operation is associated with a product. I think we said that a few times. It's important. Let's see if that makes any sense. If we have a truth table, XB, XA, XF, 0, 1, 0, 1, 0, 0, 1, 1. If we have input B is 0, input A is 0, the product of 0 and 0 is 0. The product, which is to say when you multiply 0 and 1, you get a 0. Multiply 1 and 0, you get a 0. Multiply 1 and 1, you get a 1. Right? So a product. The AND operation is a product. The last way we could think about the AND operation is English. And you might have a machine that would start when both condition A and B are true. For example, you might have a pump. That pump will only start if the discharge valve is open and the suction valve is open. To do otherwise would cause damage. All right, let's work this backwards. We talked about an English description of the AND gate. We talked about Boolean algebra, where we said the AND operation is a product. 2 or more things multiplied together. We talked about logic gates. And we said that is the symbol. You can have as many inputs as you like. We talked about, let's see, ladder logic. Ladder logic. I believe that was it, and that's enough. Okay. That allows us to talk about the OR operation. In ladder logic, we would show it this way. We have an input associated with memory location A and a Boolean input associated with memory location B. And once again, we'll send that to a coil F. The truth table looks like this. So we have B, A, output F, 0, 1, 0, 1, 0, 0, 1, 1. And the way the OR circuit works is if either of the inputs is true, the output will be true. So 0, 1, because A is true for that row. Here B is true. Here both are true. This is the schematic symbol for an OR gate. Again, you can have multiple inputs if you like. This can be built with multiple inputs. There we see 3. We mentioned the size of the truth table. So the size of the truth table is 2 to the nth, okay, where n is the number of inputs. So our 3-input OR gate would have 8 different entries in the truth table, and a 4-input OR gate would have 16 different combinations. The OR operation is described as a summation. All right, so we'd call that a sum. We saw this in the truth table. We said 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is a non-zero value, in which case we'll write a 1 to the coil. Here's an example. We'll let this be Boolean input A. We'll let this be Boolean input B. And we'll let this be, again, coil F. If we were to draw a truth table for this, input B, input A, output F. Here are the different values that the inputs can take. And now we look at the coil and we say if, oh, forgot one thing. Let's let that be a normally closed contact. Let's go ahead and enter the values into the truth table. If B is relaxed, okay, if B is relaxed, there will be continuity through this path. So if B is 0, we're going to get a 1 here. And the second row in this truth table is the same thing. B is 0, so there's continuity there. If B is a 1, well, there will be no continuity through the lower path. Now we have to look at A. So if A is 0, that means there's no continuity in either path. For the last row, if A is 1, there will be continuity here. So that is the truth table for this particular OR gate, except that this OR gate has one of the inputs inverted. Our next stop is to talk about the NOT operation, otherwise known as the inverse function. And the truth is, I've been dancing around this for quite some time, but we should explore what it really means. So we're going to call this a input A. We're going to call this coil F. So this is a normally closed contact, otherwise known as an examine if open contact. There will be continuity across this contact if the relay is in its resting position. So that means if there is a 0 in the memory location, this will evaluate as true. If we go back, I think some point we drew a picture, didn't we? Let's go find that picture again. It's up here somewhere. There it is. The rule was look at a memory location and then set the true-false lever based on this map right here. Okay? This was for the examine if closed function. We could change this to an examine if open function, And all we have to do is swap these two values. Right? And now we change this from an XIC to an XIO. So examine if open. We originally associated the word closed with a memory location that held a value of 1. Now, when we're talking about the XIO function, we're associating or we're looking for a memory location that has a 0 in it, a resting spot, and we call that 0, we call that open. Okay, so same operation, we just changed the table describing what the person inside this box does. The truth table for our NOT operation is like this. A can take on the value of 0 or 1. When we go to put the value into F, it will be stored as a 1 or 0. The logic gate looks like this. The Boolean would be written this way or this way. So if you're handwriting, you put the bar over the top of your input. If you're in text, you typically see this tick mark like so. Here's an example. We have an input B. We have a Boolean input A on a normally closed contact and our coil F. We would describe this as F is B, not A. Okay, this is a AND operation, so this is a product. F is assigned the product of B, not A. In digital gate symbology, it would look like this. This is input B, this is input A. This is A not, and this is B, the product of B and A not. That was a lot of writing. Let's put it into tabular form so we have a nice convenient place for everything. So we talked about the AND, the OR, the NOT, and we'll add a few more as we go along. So this was the product of B and A. It had a gate representation like so. If we had a 2-input device, it would have a truth table like this, where this was false for all conditions unless both A and B were active. And for ladder logic, it looked like this. Okay, so that's everything we know about the AND gate. The OR gate, F is B or A. It had a gate level representation such as this. The truth table, 0, 1, 0, 1, 0, 0, 1, 1. We see that F is assigned a value of true if either A or B evaluates as true. The ladder logic looked like this. That brings us to the inverse operation, where we say F is equal to A not. The symbol looks like that. The truth table is very simple. Okay, it just takes whatever A is and inverts it. The ladder logic consists of a normally closed contact feeding a coil. Let's give ourselves a little more room here. You could also do it this way. And I'm going to caution you against this, at least when you're getting started. This here is called a reversing coil. And you'll notice there's a slash inside of the coil. Okay, so that means whatever would have been assigned there, we will assign the opposite value. Just be careful with that. It's so easy to miss that little slash in there, and if you miss it, you could spend hours troubleshooting your code trying to figure out why it doesn't work. While we're here in the table, let's add a few more logic gates. We can talk about the NAND, so the not and. So the output is equal to the product of B and A, but there's a bar across the whole thing. And what we've done is we've taken the AND gate, which looked like this, and we've put an inverter after it. Except you wouldn't draw it that way. Instead, you would just put an inversion bubble right there. Okay, so that says take and do the AND of A and B, and then invert it. This is the truth table. It's very easy. All we have to do is look at what was over here for the AND gate, and where there's a 0, put a 1. Where there's a 1, put a 0. So 1, 1, 1, 0. So that is the NAND gate. If we can have a NAND gate, we can have a NOR gate. And you probably already know what that looks like. So F is assigned the value of B or A, but then you take the inverse of that. The gate looks like this, with an inversion bubble right there. Here's the truth table. And once again, we go over here, we go to the OR gate, and we're just going to invert every number in that table. One more gate while we're here, and that is the exclusive OR. So F is assigned the value of B circle plus A. The gate level representation looks like so. So it's an OR gate with an extra bar on it on the left side. The truth table, B, A, F. The exclusive OR could be thought of as a difference gate. So you have input A and B. If they are different, then we will assign F the value of 1. So here they're both 0, 0, so we get a 0. Here they're both 1 and 1, so we assign a 0. But in the middle, they're different. Notice that there are 2 entries in this truth table. Okay, knowing that, we can draw the ladder logic like this. We could say we have Boolean B is a normally closed contact, Boolean A, and down here we have Boolean B, and then Boolean A as a normally closed contact, going off to coil Boolean F. This row in the truth table is represented by this. So if B is resting, but A is active, then there will be continuity across this rung. And this is the second one. If B is active, but A is resting, then the coil F will be assigned a value. Before we forget, let's give this structure a name. Now, we already know the logic that it does is called the exclusive OR, but we're talking about the structure where we have this product, right? These 2 products coming together as a summation, right? In fact, we're going to call this the sum of products. I jumped up and down in this a few times, where we talked about the AND operation as being products, and we talked about the OR operation as being a summation. So when we draw this circuit, we talk about this first piece, right? This piece right here is an AND operation. That is a product. This is another product, right? Because AND operations are products. Our next step was to put them together to drive a coil. This piece is a summation, right? It's an OR operation. So we could talk about the sum of products. So our exclusive OR could have been written this way. So B naught A or B A naught. In the middle, we have the summation, which is this piece right here, right? That's the summation. And on either side of that OR, we have the products. So there's one there, and there's one there. So we talk about the sum of products. Let's consider this by converting a truth table to ladder logic. We'll let our outputs be 1, 0, 0, 1, 1, 0, 0, 0. Okay. And if we look at this, we see that there are 1, 2, 3, what we call implicants. Right, so there are 3 products in here that we need to worry about. So the first one is 0, 0, 0. The next one is 0, 1, 1. And finally 1, 0, 0. That is the ladder logic that we need to make. We could express this in Boolean algebra as C naught, B naught, A naught. But you have to be really careful when you draw this, because you need to show that the bar is only over the individual inputs, right? Because it means something completely different if you have one bar across all of them. Okay, so there's the first implicant, or the second one, which is C naught, B, A. And then the third implicant is C, B naught, A naught. In ladder logic, it looks like this. We have C naught, B naught, A naught. Okay, so if everything is resting, if everything is 0, right, that's what that means. If everything is in its normally closed position, this rung will evaluate as true. Our next implicant was, let's see, C naught. I should label these Boolean C, Boolean B, Boolean A. All right, where were we? So now we have C naught and B and A. Okay, so that takes care of that. And the last one was if C and B naught and A naught. That's that one. Okay, so this is the sum of products. These are the products. So we have 3 products in this case. And the summation occurs right here. Right? The sum of products. Since we're here, we may as well show the gate level representation of that. So we have 3 AND gates. We're going to OR them together. Now for the inputs, I'm going to cheat here. I'm going to use the inversion bubbles on an input. So this is C, B, and A. So this one here will respond to the value 0, 0, 0. This one, we have C, B, and A. So this one will respond to 0, 1, 1. And finally, we have C, and then B and A. So 1, 0, 0. Right, the output of this AND gate will be high when we have C is equal to 1 and A and B are equal to 0 because of the inversion bubbles. Once again, we have products and we have the summation brought to you by that OR gate. We'll do one more and then we'll call it a day. We have input D, input C, input B, and input A to coil F. On another rung, we have D, nothing, nothing, and we have input A. And on the last rung, we have input C, not, And that's it. Here we have 4 inputs, and we want to convert this to a truth table.
Let's see if we can do that and get it all on one page. So D, C, B, A, and F. So 0, 1, 0, 1, 1, 0, 1, 0, 1, 2. Nope, we're not going to fit this on one page, sorry. Maybe we'll get the truth table on one page, though. Now we take care of B. And you can kind of see the pattern as I go along here. That's going to be 4 zeros and 4 ones. And D will be 0, 0, 0, 0, 0, 0, 0, 0. And it'll be 1, 1, 1, 1, all the way down.
Okay, and we talked about this. We said that if you have 4 inputs, you're going to have 16 values in your truth table. Let's see if we can make some sense of this. By the way, let's make that a normally closed contact just to make it more interesting. Let's look at the last rung here. Let's look at input C. If it's resting, which means it has a value of 0, we will see that F is energized. Now that occurs here. Right? These are all the locations where C is 0. So that's here and here. Now we look at this middle rung, and this tells us if D and A are both active, then coil F will get assigned a 1. So if D, so that's this here, so this is if D, and if A, so A, so that would be here, 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 and here. Well, those are already assigned, so this would be a 1 and a 1 there. The last one, if D and C and B, but not A. If D and C and B, but not A, this will be assigned a 1. For all others, it will be 0. Okay, so there we've done it. We've converted a, let's see, where'd it go? We took a truth table and converted it into ladder logic. We also converted it into a gate level representation. Then we took a piece of ladder logic and we converted it into a truth table. Well, I think that's enough for one day. When you come back, we're going to talk about application examples. And we're going to spend a lot of time working on that simple English that I mentioned, because it turns out that it's, well, okay, it's story problems.